Welcome back. This is a recap of the introductory session to season 2 of Extremely Open Science. And the first thing I've done since this session is I fixed my audio because I had, so we're back in the office, and the first day back in the office, I messed up the audio configuration, and actually I didn't turn off the crummy microphone that comes with the laptop. And so we had both the good the good microphone and the crummy one. And that gave an echo effect, and I thought it was an echo, but it was just actually a misconfiguration. But let's get back to the science, and we did this very different session because the first half of the session was just talking about what the project is going to be. But I'll give you now the 10-minute version as opposed to the half-an-hour version that we had during the session, because I already drew these things. So let's say this is what you have here. This is your real life genome. So not MAG, this is your real life genome. Oh, actually, your real life genome has a C there. Your real life genome has a C there, right? And it has this coding sequence, that's a functional coding sequence. And then we go in and we sequence it. And this is something that happens especially with long read data, with nanopore data, and we're big fans of nanopore data, but it does lead to these issues where, here the C is gone, right? This C here that existed there, it's gone. And so what does this mean? This means that now this coding sequence, when it still has here this start codon, right? So it's the coding, that's correct, and then this codon is correct, but then when we get here, we have a frame shift because the codon is missing here nucleotide, and so now it gets misread. And so first of all, everything here, this is going to be gibberish from the protein point of view, and then we will eventually reach a stop codon, because if you have random DNA, you have stop codons just randomly, and it's actually so functionally protein coding genes, there's selection to keep these from popping up. And so here's the real stop codon there at the end, but we're going to have there. So this will be an apparent pseudogene, so some sort of, on the mailing list I also call it the pseudogene. I'm going to be calling them apparent pseudogene. So this means that it's not a real pseudogene, but it looks like one. And there was also this paper that came out, and I've shared it before, from Cooley and Wright. And this is such a great paper. I really love this type of papers that are, at the same time, just a very clean message, very well done. They have a clear statement, and then they support it well, and that's, it's very nice. And as part of their conclusions, they write, this is the last sentence of the conclusions. Our results suggest that high read coverage is required for correct assembly. Okay, we agree there. And then next, and indicate an inflated number of pseudogenes due to internal stops is indicative of poor overall assembly quality. And so in this half sentence here, this is the basis of this project that we're going to be developing in season 2 of EOS. Is can we estimate this inflated number of pseudogenes due to internal stops and use this as an overall indicator of assembly quality? And so and going from this high level, a little bit hand wavy view is going to be what we're going to be doing, right? So maybe backing off a bit. So we saw this looking at Anna Kusko's data, where she's been working with metagenomes from pet dogs in Shanghai, and we saw. So, and we were using CheckM, CheckM2 to get estimates of quality. And so it's a good question to ask. So what happens, how does CheckM deal with this? So CheckM 1 and 2 work differently, but they both look at specific important protein coding genes. So CheckM 1 looks at these single copy marker genes. And so if our gene, our parent pseudogene from the previous slide is now missing, because this is it, then CheckM1 will, it's very easy to see. It will say, okay, it's not complete because I expect this to be there and it's not. Check-M2 is a little bit more complicated. I think the intuition I have for it is that it learns that there are groups of genes that go together. So maybe it learned that A and B go together. And so if it sees A, but then it doesn't see B because B is now this pseudogene, it's going to mark it down as lower completeness. And so this is what we think happens because, so in our data, so we have ONT, so ONT is Oxford Nanopore Technology, so long read data, and we also had Illumina. So in the way we handle this, and I think this is fairly standard, is that we built assemblies using the long reads, and then we polish them using the Illumina. And in some cases, not all cases, but in some cases, and these are particularly the lower abundant genomes, we saw a huge jump in completeness. So for cases, this is so we go maybe from 80 to 90% when we go from Oxford Nanopore to the polished version. So here a jump of 10 percentage points, and this polishing doesn't actually add novel sequence. So if we had at the beginning we've had 4 million base pairs, here we still have 4 million base pairs. We don't have 4.4 million base pairs. It's not like we're adding 10% more sequence. So what we think is happening is that in this case we are correcting these errors. So we are adding these missing genes. So if here there was a fake stop, now we've fixed the fake stop. Here, we add this missing genes, right? So the other thing we see is that the average gene length goes up. So this makes, so genes are just longer. So longer genes are better. So this was probably where we started to look at this. Then we also saw the Coolin and Wright paper that came out. It just came out more or less as we were thinking about these things. So sometimes just things hitting at the right moment, and so these ideas were there, but obviously this is one genome, so we're comparing sort of two versions of the same genome, because other genomes have different average gene sizes, so we cannot use average gene size, and we have other work looking, for example, at small proteins, and some proteins are just small, and some genomes are just enriched in small proteins, and so they will have small genes, and that's not because they are bad. That's because that's their function, or that's how they've evolved, and so we cannot use overall gene length. So we've had a couple of ideas on how to make this a little bit more precise. So here just so one is if we really have these frame shifts in the middle of a gene, so things should look like this. So we should have the start of the gene, and at the start of the gene, things should be very well conserved. So this should match reference versions very well, and then at some point gibberish and a stop. So this is a pattern that we can maybe try to look for. Very well conserved, then gibberish and a stop. This would be a pattern, and potentially we could even check if it's fixable. We just is there like a one or two frame shift that we could introduce that would then now make everything be well conserved at the beginning that it is, then some fixed region, and then well conserved with respect to the reference as well. And the other idea is, okay, so we have, let's say this is our gene, let's say it's 300 base pairs, 300 amino acids. So if it's 300 amino acids, we don't know, maybe that gene is 300 amino acids, maybe that is what it is. But if we can map it to a family of genes, so for example, to orthologous groups from eggnog or something like that, and let's say in that family, all the members are 500 to 600 amino acids long. So this is about half of the size of the typical one. So in this case, this is now indicative that we do have a truncation here. Right, so these are some ideas that we would like to explore. But before we get that, the first step is to try to validate this a bit based on simulation. So we're going to take a good genome, or good genomes eventually, and then we're going to add indels. So this is all in silico. We're going to create these mutated versions, then we run it to checkm and potentially other tools, and then see what happens. And so in here, this is my expectation is that we will see something like this. So as the indel rate increases, so at first nothing much happens, and then eventually it starts to crater, and it eventually goes to zero, right? If you eventually just have every single gene is rubbish. So in that case, something like checkm2, which relies on gene calling and protein gene calling, it will see nothing. It will just see a bunch of rubbish, but I think it will be interesting, first of all, to know where is this point here, where things start to collapse, and to know if really there is a plateau or if it's more linear. In some sense, if it's more linear, this maybe takes away from the value of our tool, of our proposed tool, because if checkm2 is already capturing this, then maybe that's it. Maybe checkm2 is already implicitly works really well for detecting in the high indel rates. But maybe if there is this plateau, maybe there is a region here where this genome is already not great. It already has a high rate of genes that are messed up, but checkm2 is still not able to capture that. So in this case, this would validate the value of the tool as well in that perspective. So from my point of view, it's interesting either way. It's really also just very interesting to just be able to do these estimations in any case, and then it's a bit of an empirical open question whether it adds value from if you're just thinking from the purely will it be able to filter out genomes that current tools like checkm2 cannot. Right, so we went through this on the stream. Also discussed how this is a much more of a Oxford nanopore era problem. Back in the Illumina era, which was maybe 6 months ago, we didn't really have this. Because back then the big problems and a lot of these tools like checkm2 and or junk, etc., were designed with the thinking that the typical errors are either you've not been able to assemble something, just things didn't assemble, or they assemble but you didn't put the contigs correctly, and so I think this problem of they've assembled, the contigs are correctly put together, but you have a very high rate of small mutations, either single point mutations or frame shifts, and frame shifts are much more deleterious to this issue. If you have a single point mutation, normally your protein is very likely still going to work, and especially these more computational approaches of trying to, for example, do functional prediction, they will still generally work if you have one point mutation in the middle of a protein. But a frame shift messes up everything after it. So if I have a frame shift in the middle of or early in a gene, that everything else is messed up. So we looked at this. I looked at pointed again at Cooley and Wright, and then we started a project, and I said I'm going to be calling it Sardine. There's really no reason. Maybe we'll call it something else. Partly it's because we do have this other tool unrelated that's called Macrel, and Macrel does stand for metagenomic AMP classification and retrieval, but Macrel is also a very old-fashioned spelling of mackerel, the fish, and sardine with a Y is a very old-fashioned spelling of sardine, the fish. And since those are two similar small fish, actually I believe that sometimes mackerel is sold as sardine. There's a lot of fish fraud, but this is not a fish fraud stream. This is a bioinformatics stream. So I also checked that there's no other bioinformatics tool called Sardine spelled like that, which is so. Given that it's pronounceable, we're going to call it Sardine spelled with a Y. So we did that. We created a repository which I've pushed, and you can find the link in the description. And wrote a little jug script to download the data. To download this genome here, Escherichia coli. Spent a little bit of time trying to spell Escherichia, very hard. That's why you should always call it E. coli, so you don't have to spell Escherichia. And yep. So this is a probably, this is a single contig genome. This is the representative single contig, so it's a very high quality genome, and so we will start there. And then we will start mutating it to create lower quality versions, and in a controlled way. So we created a README file, added a copy, added some notes to start up, created an environment, added just a bunch of things we're gonna probably need. So checkm2 requires a lower or older version of Python, so we will install it in another environment. So that's all problems for next week. Right. So that was it. So that was the initial stream we have. So I will post this on the mailing list. I'll post the recap up. Sorry about the sound. For don't watch the recap, or watch the recap. Don't watch the replay of the live stream, because I fixed the sound. Next week I will not make this mistake again, hopefully. All right. So see you then. Any comments on the mailing list? And so I hope to see you soon.